Welcome to Factory on Air by DBR77, where smart manufacturing gets real. This is episode 24, Quality Under Control, How to Reduce Complaints and Improve Customer Satisfaction. Quality isn't just what happens at the end of the line, it's what happens every second on the shop floor. In this episode, we explore how real-time monitoring, IoT, and AI help you catch quality issues before they leave the factory. You'll hear how DBR77 empowers operators, flags anomalies instantly, and enables predictive action, not damage control. It's time to make quality proactive, measurable, and integrated into every operation. Factory on Air is powered by DBR77, the platform that turns quality from inspection into intelligent prevention. Let's begin.
Welcome back to the deep dive. Today we're focusing on a topic that really sits at the intersection of, well, everything that matters in manufacturing. Operational cost, customer satisfaction, and some really high-stakes engineering. We're talking about quality control.
But not the old way of doing things.
No, exactly. We're not talking about some archaic system where you have someone with a clipboard checking things off at the finish line. We're here to sort of tear down that traditional and frankly insufficient model.
Indeed.
Yeah.
I think our sources frame the modern industrial reality perfectly. Quality isn't just a final checkpoint anymore. It's become, as they say, a continuous daily battle for details.
The battle for details. I like that.
Right, because when you're operating in these global markets that demand near perfection, that traditional retrospective approach, the defect-depective model, just fundamentally broken.
If you're waiting until the product is packaged, or even worse, until the customer calls you 3 weeks later, you've already incurred the maximum penalty. You've lost.
You've already lost. So our mission in this deep dive is to explore how the most advanced technology, the synergy of the Internet of Things, robust real-time data, predictive AI, is completely reshaping this process.
So we're moving from just detection to actual prevention.
True prevention.
Yeah.
The goal here is clarity. It's about understanding how to spot production problems before they ever leave the factory floor.
Right.
And by doing that, establishing automatic, preventative, and corrective actions that genuinely measurably reduce claims, warranty costs, and, customer churn.
And then this isn't just a nice-to-have upgrade. This is critical knowledge for survival today.
Absolutely. This is essential for any organization that's looking to slash those massive and often hidden operational costs.
Hidden is the key word there.
It is. We're talking about minimizing waste in these incredibly complex, multi-stage global supply chains, and most critically, securing those high-value, long-term customer contracts.
Because if your competitor can do it better...
If your competitor can guarantee a 30% lower defect rate and get innovations to market faster, they win the business, period.
So over the next 30 to 40 minutes, we're going to unpack the common, insidious failures that plague these older systems. We'll look at the revolutionary power of continuous data streams, and then show how moving toward a holistic digital platform really links quality directly to strategic business growth.
How it gets embedded into the entire DNA of the enterprise.
Exactly. So let's start with the operational pain points. We all know things go wrong, but why do these failures persist, even in what are supposedly well-run facilities?
I think the core flaw in traditional quality control is structural. It's retrospective. The problem only really surfaces at the very end of the production line or, disastrously after the product is already shipped.
Too late.
Far too late. And when we really analyze the industrial landscape, we see 4 persistent blind spots emerge. And they're all rooted in a delay of detection or a severe lack of immediate contextual data.
Okay, let's break down that first one. It's the one that often gets blamed entirely on, bad training or carelessness, but it sounds like it's actually a systemic failure.
That's the core misunderstanding right there. The first frequent source of quality failure is operator errors. And crucially, these errors often stem not from apathy, but from a fundamental lack of up-to-date, current, and accessible instructions.
Okay, so give me a scenario. How does outdated information lead to a measurable defect on the line?
Okay, imagine a complex assembly line. Engineering mandates a new lubricant specification, or maybe a slight change in the torque sequence for a critical component.
Happens all the time.
All the time. This new process is documented. Maybe it's in a PDF that was released last week. But the operator on the floor, they're still relying on the paper printout from 3 months ago.
Or some manual on a shared server they have to click through 10 times to find.
Exactly. And that sheer gap between the outdated documentation and the dynamic reality of the production floor, that's where the mistake happens. The person is trying to follow the process, but the system hasn't supported them with the current context at the point of action.
So it's really a documentation delivery problem that's just disguised as a training failure.
That's a perfect way to put it. The system needs to support the operator with current, contextual, maybe even interactive guidance.
Right. So if the terminal they're working at showed them a visual guide based on the specific product running right then.
The error rate would drop dramatically.
Exactly. Okay, now what about the machines themselves? Even if the operator is following perfect instructions, the process itself isn't always stable, is it?
Not at all. And that leads directly to the second major issue, invisible parameter deviations. Modern machinery, CNC mill, an injection press, an advanced welding robot, it runs on extremely subtle, precise metrics.
Temperature, pressure, speed.
Flow rates, vibration frequency, all of it. And these parameters can subtly shift outside that ideal operating window. Maybe just 1/10 of a degree or a marginal change in PSI.
But it's still technically within some wide historical tolerance band, so no alarms go off.
Precisely. And if that subtle shift isn't immediately flagged, the damage just compounds.
Right.
If your monitoring relies on periodic manual checks, or if the sensor suite isn't integrated to provide continuous high-velocity data, these shifts go completely unnoticed. They stay invisible until they accumulate into a catastrophic or a pervasive defect.
Like a stress fracture or a weak weld.
Or delamination. By the time that final defect is discovered, the process has likely been producing substandard product for hours. The defect is the symptom, but that subtle, invisible deviation was the cause. And it was missed.
It was missed because of a lack of continuous monitoring. So the detection system is just too slow, which I guess leads directly into our third common failure point, delayed discovery.
Absolutely. The third failure is delayed detection. And it's because of a reliance on inadequate in-process or final gate control. Many operations still treat inspection as a final checkpoint.
So a defect that's generated at, say, process step 3
is only confirmed at the final inspection station, which might be step 15.
That lag just sounds incredibly expensive.
It is a massive waste of resources. That lag means two critical things. First, you've wasted significant time, energy, and material.
You're adding value labor, coatings, secondary components to an item that was already scrap.
It was already scrap. And second, because of the production rate, you now have a backlog of potentially hundreds or even thousands of defective items that were made in the hours between when the failure occurred and when the final inspection finally caught it.
The cost just escalates exponentially the further downstream that defect travels.
It really does. And then once you find that pile of defects, the fourth flaw kicks in, and this is the killer. You can't figure out what actually caused it quickly enough to matter.
So you can't do a proper root cause analysis.
Right. The fourth failure is the inability to perform timely and accurate root cause analysis. Because the data is missing, it's fragmented, or it's scattered all over the place.
So you find the defect, but you can't immediately trace back the exact history of that specific unit.
Exactly. Which machine touched it? What was the precise air pressure at that exact moment? Which batch of raw material was involved? That crucial historical context is often trapped in paper logs, isolated databases, or different legacy software systems that don't talk to each other.
So you end up just treating the symptom instead of the actual disease.
That's it. You apply a generic fix, maybe you recalibrate the machine broadly, but that doesn't address the true underlying trigger, which means the defect is highly likely to just reappear next week.
You need instant access to a unified, traceable history.
You do. So if we step back, the aha moment here is that quality control can't be seen as a retrospective detective task anymore. It can't rely on periodic checks.
It has to shift entirely.
It does. The core realization is that fixing quality requires a system that provides immediate visibility and actionable data. We have to move the focus from just reporting what broke yesterday, which is only useful for liability and accounting,
Right.
to actively and predictively preventing what is about to break right now. Operational excellence demands predictive action.
Which is the perfect transition. The systemic failure in detection leads us directly to the solution framework you're talking about.
It does. The necessity of leveraging integrated technology to achieve true real-time monitoring.
And this is where the Internet of Things, or IoT, transforms from just a buzzword into the absolute backbone of manufacturing operations. It's the mechanism that generates that river of data we need.
Precisely. The solution is leveraging the Internet of Things and seamlessly integrated machine systems. This involved fundamentally changing how you collect data. You're shifting from manual periodic spot checks to constant high-velocity data streams generated directly by thousands of sensors and networked industrial machines.
Okay, but that sounds like a massive amount of data. How does a company ensure that this stream of data is actually useful and not just, digital noise?
Usefulness relies entirely on two things, context and velocity. We are talking about data collection at every single operation.
Yeah.
Every measurable action, every tool change, every thermal cycle has to be captured without any delay.
And the mechanism is designed to link those parameters directly to what? What's the context?
That's the critical part. If a traditional system just logs, machine 4 temperature reading 95 degrees, a modern system logs that reading, but it also tags it instantly and automatically with 5 crucial identifiers.
Okay, what are they?
The specific product ID being made, the batch or lot number, the unique machine ID and its operational status, the operator ID running the line, and of course the timestamp.
So you get this incredibly granular, traceable quality history.
An entirely auditable and traceable history,
Yeah.
which is essential for that rapid root cause analysis we were talking about.
And that level of instantaneous context is what drives the power of immediate alerts. That's where the massive cost savings come from because you stop the problem immediately.
Absolutely. This is the difference maker. Alerts are generated automatically the very instant a parameter deviation is detected. It completely bypasses the slow human inspection cycle.
So give us the hard contrast there, the old way versus the new way in terms of cost.
Okay, think back to that delayed detection flaw. In the old batch check model, a machine might slowly drift out of its acceptable calibration over, say, 2 hours. The operator, or maybe a final inspector an hour later, catches the issue.
Okay.
At a high-speed production rate of, let's say, 50 units per minute, you might have just produced 6,000 defective items.
Wow.
And they now require complex rework, or you have to scrap them, costing hundreds of thousands in material and labor. It's a catastrophic loss.
Okay, so contrast that with the modern system.
With the modern integrated system, it detects the parameter exceeding a micro-defined threshold. Not that old wide tolerance, but the ideal operating window, and it generates an alert within seconds. The machine might have only produced 1 or 2 items when the alert fires.
So the system either adjusts itself automatically or flags a human to intervene immediately.
Exactly. And the cost difference between scrapping 2 items and scrapping 6,000 items, well, that's the entire argument for this digital transformation.
It turns quality costs from this massive, unpredictable variable into a controlled, predictive investment. But what about the management perspective? Once you have this constant stream of data, how does a manager turn that into strategic intelligence?
That's where operationalizing data analytics becomes so crucial. The centralized platform registers all this quality data defects, near misses, deviations, in a standardized, easily searchable format.
So because every piece of data is tagged with all that context.
You can perform really sophisticated filtering and analysis. Instead of a vague defect report, you can ask the system a very targeted question.
Like,
you can filter data instantly by error type, by a specific component supplier, by machine, by the day of the week, or by shift team.
so if you notice dimensional errors are spiking every Monday morning,
You can instantly narrow the problem down. Is it a cold start procedure? Is it specific material handling? Is it something a particular maintenance crew did over the weekend? This speed and granularity accelerate that root cause identification dramatically.
so you move from just saying, we have quality issues, to asking a really precise query.
A surgical query, like,
Yeah.
why is the second shift using this specific welding robot experiencing microfractures during the first hour of production on days that follow a major tooling change?
That allows for a surgical intervention instead of some costly, broad operational change that might not even fix the problem.
It creates a feedback loop that's immediate and self-optimizing. You're using the failures of the past hour to prevent the failures of the next minute.
We've established that real-time data collection solves that problem of immediate detection. But as you mentioned, the true endgame here is prediction. And this is where artificial intelligence steps in, moving us beyond just logging errors to actively anticipating them.
Prediction really is the pinnacle of process mastery. If IoT gives us sight, AI gives us foresight.
I like that analogy.
It changes manufacturing flaws from, inevitable risks to manageable variables.
So how does AI actually do this? How does it ingest this massive granular river of quality data and turn it into actionable anticipation? We need to get into the how.
Well, it employs highly sophisticated statistical and machine learning algorithms. Often, it's leveraging deep learning models for anomaly detection and correlation analysis. It analyzes that quality data across three critical dimensions that a human analyst just couldn't process simultaneously. The volume and complexity of the variables are just too great.
Okay, let's start with the hardest one. The links that nobody sees.
That's the first dimension. Detecting non-obvious dependencies. A human operator might intuitively know that high ambient temperature and high machine speed increase the probability of overheating. That's a simple linear connection.
Right.
But AI can uncover hidden, subtle, nonlinear links. For example, it might realize that a combination of the specific viscosity of the cooling oil,
A metric from an external sensor.
right, coupled with a slight individual operator adjustment to a feed rate, which is logged in the execution system, results in a 15% increase in part porosity 6 hours down the line.
Wait, hold on. If the viscosity change and the feed rate adjustment are both individually within their acceptable tolerance bands, how can the AI spot the issue?
That's the power of these anomaly detection models.
Yeah.
It doesn't look for parameters going out of bounds. It's looking for patterns that correlate strongly with known defects, even if the individual inputs are technically fine.
So it flags the unique combination of these seemingly benign variables as a kind of threat signature.
Exactly. It uncovers correlations between completely disparate processes. It might realize that fluctuations in the raw material humidity storage unit directly impact the surface finish quality on the final assembly line, which is miles away.
That's fascinating. That's true process mastery. So what about spotting failure signatures that we have already seen before?
That's the second dimension, identifying recurring patterns. Machines don't just catastrophically fail out of nowhere. They send signals beforehand.
Right.
AI excels at recognizing common failure schemas or these subtle, complex, multivariable sequences that precede a major quality event. It learns the signature of a motor that's starting to wear down or a press that's beginning to drift out of alignment days before a human maintenance schedule would ever flag it.
It's deep pattern recognition, far beyond just simple trend analysis.
Somewhere beyond. And combining those two leads us to the critical function.
The threat prediction.
Correct. The ultimate goal is threat prediction. By synthesizing those non-obvious dependencies and recognizing recurring patterns, AI can assign a real-time risk score to every batch, every product, and every process step. It identifies potential risks before they escalate into a noticeable flaw.
Which reduces the likelihood of a customer complaint or a warranty claim to near zero.
And that's the outcome. A proactive prevention strategy that fundamentally changes how a business even budgets for quality.
How so?
Well, we move the expense from remediation, field service, and liability, which are all variable, high-cost operational expenses, or OPEX to optimization and prevention, which are controlled capital investments, or CAPEX.
That preemptive action allows companies to initiate countermeasures before the customer is even aware a problem was ever possible.
Precisely.
But this requires a lot of trust in the automated system. When the AI model confirms a threat, what specific immediate programmatic reactions does a modern quality module deploy without needing a human to sign off?
This is where you need robust, immediate response capabilities. A modern system just can't wait for an employee to log in or for a shift change.
So detail those automated reactions for us.
Okay, first, automatic line stoppages are mandatory. When parameters exceed critically defined thresholds, or when that AI threat score crosses a certain danger line, the process stops. Instantly.
No questions asked.
If a variable could cause a catastrophic failure or massive defects, you stop. Second, there are instant notifications that are tiered and routed to the exact relevant department. Maintenance gets the hardware warning, quality control gets the deviation report, production management gets the throughput alert.
And a third, most advanced reaction.
That would be the action recommendations based on AI-driven data. The system doesn't just say stop. It says stop, adjust feed rate X by negative 0.3 units, and initiate mandatory tool check Y, referencing SOP 402.
So the advantage isn't just the speed, it's the certainty and specificity of the action.
The key advantage is reliability and consistency. The reaction is immediate, it's consistently applied across all shifts and all plants, and it's independent of employee fatigue or experience or even availability.
And that consistency maximizes recovery potential and minimizes damage every single time.
Every time.
That level of automation, though, must raise questions about integration complexity. I mean, if a company has decades of legacy machinery, How realistic is it to integrate all this sensor data to feed the AI? That sounds like an IT nightmare.
That is the critical hurdle, and it requires platforms designed specifically for industrial integration. The process really starts with standardization. You have to create a uniform data language across all of these disparate systems.
And how do you do that?
Many advanced industrial platforms offer middleware specifically to translate legacy sensor outputs into the standardized data streams that IoT and AI analysis require. It's challenging, for sure, but it's achievable through strategic modular implementation.
So you don't have to rip and replace everything at once.
Absolutely not. You strategically apply integrated sensors where the quality risk is highest first, and you build from there.
Okay, so we've established the mechanics of real-time data and AI, but the strategic impact of these systems, it only fully materializes when we elevate them out of just the realm of compliance.
And integrate them into the larger strategic context, the comprehensive digital transformation of the entire enterprise.
Let's ground that mission. Why is this transformation so necessary right now?
The overarching mission is really driven by global competition and accelerating market dynamics. Traditional industrial processes, which are often siloed, slow, and opaque, are just no longer viable.
They can't keep up.
They can't. Transformation means achieving higher efficiency, complete transparency across all operations, and fostering the innovation that's necessary to meet these highly dynamic customer demands. Simply put, relying on old, analog, or disconnected methods is a recipe for obsolescence.
And quality, which was traditionally seen as a necessary cost center, now it has to become a central pillar of this transformation.
It has to. Advanced digital platforms are explicitly designed to integrate quality execution seamlessly with enterprise resource planning, with production execution systems, with maintenance operations.
So quality becomes part of the process flow, not just a final check.
Exactly. This holistic approach means that every single decision, from raw material procurement to scheduling a batch, is informed by the most current, real-time quality intelligence.
One of the most powerful tools for achieving this holistic view is the concept of the digital twin.
The digital twin is absolutely a foundational pillar. It's what makes predictive quality truly operational.
I think many people understand it as a 3D model, but they might miss its dynamic utility. Can you explain the full operational function for us?
It's so much more than a blueprint. A digital twin is a complete, living, virtual mathematical model of the entire physical production plant or logistics center.
A living model.
Yes, and its power comes from combining advanced 3D simulation capabilities, which allows for that highly accurate visualization, with the continuous high-velocity data streams fed by the IoT sensors we just discussed.
So it's a dynamic mirror that sort of breathes with the factory.
Precisely. It allows for real-time monitoring, advanced analysis, and most importantly, risk-free experimentation.
And that's the value proposition.
It's transformative. Users can test complex operational scenarios, like modifying machine layouts, adjusting throughput speeds, integrating a new robotic arm, and immediately predict the precise effects on efficiency, resource consumption, and quality output.
All without ever disrupting the current active production line.
Without stopping a thing. That ability to simulate without stopping the line must save millions in potential trial and error costs.
It must radically reduce risk.
It does. And for quality control specifically, the digital twin lets you identify potential bottlenecks or weak links in the supply chain flow virtually. You can run simulations to see if process A's vibration tolerance affects process B's precise alignment requirements.
So you're optimizing in the virtual world to get gains in the real one.
By optimizing material flow and testing efficiency gains in that virtual environment, the digital twin contributes directly to minimizing waste, increasing overall operational efficiency, and significantly reducing costs before a single physical change is ever budgeted or executed.
That addresses the immediate operational level. But digital transformation needs long-term strategy. How do company leaders ensure their significant technology investments actually align with their multi-year business goals?
They need a structured approach. And that's where the Strategic Digital Development Roadmap, or DRD, comes in. Digital transformation can feel like a labyrinth. You need to start, but defining the path can be overwhelming.
So what's the DRD's structure? How does it help?
Its purpose is to provide the methodological tools to first assess the company's current digital maturity across every functional area, then to analyze relevant market megatrends.
Like geopolitical shifts or new material sciences.
Exactly. And finally, to create detailed step-by-step development maps. It's incredibly comprehensive, often covering more than 27 distinct operational, developmental, and technological areas.
Okay, can you give us a concrete example? What would 2 or 3 of those 27 areas look like for a manufacturing CEO?
Certainly. One area is operational efficiency mapping. The DRD would quantify the potential ROI of optimizing material flow and energy consumption, defining clear milestones for reducing waste. Another area is supply chain digital integration, which assesses how deeply quality data from your Tier 1 suppliers integrates with your internal production planning.
So grading your ability to minimize risk from external sources.
Precisely. And a third might be technology infrastructure assessment, determining if your current network capacity and cloud solutions can actually handle the high data velocity required by all these new IoT sensors across the plant.
That level of detail must provide incredible transparency for management.
It does. For leadership, the DRD provides a transparent, quantifiable view of current operations and a clear, executable strategy for the future. It minimizes the risk of budget overruns, prevents investment in non-aligned technologies, and ensures every digital initiative aligns directly with core business goals.
It tells you exactly how far a process has come digitally and what the most profitable next step is.
It does.
We mentioned earlier that procurement can be a massive bottleneck. The source material suggests the traditional process takes over 25 months.
That's staggering.
It is a critical pain point in industrial growth. The traditional automation procurement process, from initial planning, research, tech selection, finding the right integrator, contract negotiation, implementation, optimization, it historically averages around 25 months.
2 years.
Over 2 years. In a fast-moving, globally competitive market, waiting that long to deploy a necessary efficiency upgrade can cost a company its entire competitive edge.
So how does an intelligent automation marketplace slash that time and cost? What's the actual mechanism? The marketplace is a structured digital platform. It shortens the entire timeline dramatically by removing layers of manual repetitive work and providing transparency. It facilitates rapid, transparent offer comparison because integrators have pre-vetted profiles and standardized service offerings.
And AI algorithms help with the selection?
Yes, they recommend the optimal solution, the machine type, the software provider, the local integrator, based on the company's specific needs, budget, and projected ROI. It essentially automates the complex vetting phase.
It automates the matchmaking process.
Exactly. It uses data to facilitate smarter purchasing. And this structured approach is why the marketplace is designed to cut the total deployment time in half. It brings that 25-month timeline down to closer to 12 or 14 months.
And the cost savings.
It can save up to 30% of costs during the purchasing and implementation phases alone, just by standardizing contracts and optimizing the scope definition early on. It forces integrators to focus on rapid execution rather than lengthy, opaque sales cycles.
Okay, let's move to the bottom line. We've described the technology and the strategy, but what does this integrated predictive quality model actually look like on the balance sheet? Because reducing reclamation and warranty costs is the ultimate financial imperative.
And the principle remains absolute. The earlier you detect a defect, the smaller the cost of its removal. When you shift your operations from reactive inspection to predictive prevention, you dramatically reduce cascading costs that often go unmeasured.
So let's break down where the money is saved. It's not just the cost of the material, is it?
Oh no, it's far more complex than that. You see a significant reduction in production downtime because fewer major failures require line stoppages or catastrophic repairs. You see lower service and transport costs associated with handling returns, field repairs, and expedited shipping.
And the big one?
And the big one, mitigating the risk of losing major contracts, which can run into the hundreds of millions. That is the biggest risk reduction of all.
And the data supports this.
It does. Companies who successfully adopt advanced quality monitoring often observe a real reduction in their total cost of quality, often by 20 to 30% within the very first year.
A 20 to 30% saving on overall quality costs is transformative for profitability. Can we look at some real-world application examples to see these systems in action?
We can. Let's look at the high-stakes environment of the automotive industry. Implementing predictive algorithms fed by integrated quality sensors on welding and assembly lines has enabled companies there to achieve a 35% reduction in end-of-line rejections.
Wow.
The algorithms use high-frequency vibration and torque analysis to flag micro-deviations in components before the car chassis even leaves that station.
And what about in manufacturing processes where the tooling itself is highly vulnerable and prohibitively expensive?
A perfect example is plastics manufacturing, specifically injection molding. These molds can cost over $1 million. So rapid detection of deviations, like a subtle pressure spike or a temperature irregularity, is critical.
And the system responds.
The advanced quality systems are designed not just to flag the deviation, but to automatically stop the cycle before that pressure spike causes permanent structural damage to the mold tooling. It's a protection mechanism driven by machine data.
And finally, what about complex consumer goods, where the product history needs to be maintained for years after the sale, like in the home appliances or AGD sector?
The AGD sector is a great example because of all the regulatory and warranty requirements. By integrating their quality systems with a digital twin, companies achieve full, granular tracking of production parameters for every single batch and often for every single unit.
So if something fails years later,
If a batch of refrigerator compressors fails 3 years after assembly, the manufacturer can instantly pull up the historical logs, the exact temperature, the torque applied to the mounting bolts, the atmospheric pressure during sealing for that specific component during its assembly,
that must accelerate liability assessment and root cause analysis immensely.
and future design improvements.
Yeah.
Absolutely.
Now, we've spent most of our time discussing machines and data, which makes sense, but the quality of the final product is still executed by human teams. How do these high-tech systems avoid becoming, some impersonal enforcement tool and instead actually engage the workforce?
This is a critical philosophical and operational point. The systems are designed to support and empower people, not replace them. They enhance human capability by removing the grunt work of repetitive inspection and documentation.
So the operator can act more like a problem solver and a process owner.
Exactly.
And how does that look practically for the operator on the factory floor?
Operator involvement is fostered by providing agency and tools. Instead of paper forms, operators report issues instantly via interactive terminals. They receive interactive step-by-step repair or readjustment instructions directly on their screen, specific to the immediate deviation that was detected.
No, they're part of the solution in real time.
They are. And because all the contextual data, which machine, which parameter, what time is available immediately, they can participate in a real-time root cause analysis. This focus on immediate communication and problem resolution fosters a genuine culture of quality engagement.
So operators aren't just blamed for errors anymore, they're empowered and given the tools to prevent them?
Exactly. It's a shift from being a checker to being a primary controller of the process. They're elevated from line workers to highly effective process guardians, armed with predictive intelligence.
And just to wrap this section up, let's briefly reinforce how this quality focus benefits from the other optimization tools we mentioned. It's all interconnected.
It is entirely holistic. Enhanced quality is often the most significant and measurable byproduct of overall efficiency. When you deploy tools for operational efficiency like dynamic value stream mapping or VSM and automated material flow planning,
You reduce waste and downtime.
you reduce wasted movement, inventory buffers, which inherently reduces the potential for material damage and leads to lower downtime and increased work efficiency across the board.
And even procurement benefits from the quality focus.
It has to, because quality begins with the input materials. Digital tools support procurement by automating the comparison of supplier offers, assessing supplier credibility based on their historical quality performance data, and using AI-assisted selection to choose optimal components.
So you proactively minimize quality risk before the material even enters the plant.
It completes the full circle approach from acquisition to final customer delivery.
This deep dive into the transformation of quality assurance has been a journey from identifying these painful blind spots to designing truly predictive industrial systems. Let's quickly summarize the critical takeaway for our listener.
I think the central theme is this: quality excellence is achieved through radical integration. It requires the seamless, automated connection of operators, machines, data streams, and predictive intelligence into one cohesive digital ecosystem.
So when quality is integrated, when it's part of the digital twin, part of the planning, part of the automated reaction system,
It stops being a variable cost and becomes a powerful, sustainable strategic advantage.
and you, the learner, now have the framework for understanding how to lead your organization from that outdated reactive defect control to proactive predictive quality assurance. This is how you secure sustainable competitive advantage in a world that increasingly demands perfection at scale.
Which leaves us with a final provocative thought for you to consider. If operational quality relies entirely on data transparency and instantaneous action, what hidden costs and inherent risks are currently embedded in your operations that you haven't yet measured? What is the real price of the data you don't have? The data that would have prevented the next failure?
And beyond the cost.
Beyond the cost, what critical protocols must be put in place to ensure absolute trust in the operational systems that are now recommending automated systemic reactions, like line stoppages, based purely on machine-generated intelligence? That transition requires a new form of human governance.